감사합니다. 안녕하세요. Hello. Thank you for the invitation to be here. I participated at the last event virtually via video. It's great to be here in person. Thank you so much, President Park, everybody, for the invitation. It's great to be here in person. I just want to grab a couple of points from the previous speakers before I jump into my content. So President Park opened up with a comment that we spend globally $270 billion a year on combating financial crime, and the net result is an impact on less than 1% of global financial crime. So I think the premise, which I totally support, is we could do much better, right? Just as a global industry, we're spending a lot of money and getting very little impact as a result of it. And then Professor Che talked about the great work that she's doing, but the call to action was we need more data to train better models. That's what I want to get into. And then Mr. Kang's presentation just now also emphasized this idea that the market's moving quickly, and we're short of experts, we're short of people, and so technology might be able to jump in. So hopefully my presentation will bring some of these ideas together for everybody. Okay, so can I walk around with this thing? Yeah. Wear this now. Imagine you're a surgeon, okay? You are a surgeon and you remove cancerous tumors. So this is an image or a series of images of a tumor. And what you see is an evolution of the technology to be able to detect the outlines, the borders of the tumor. So if you're a surgeon, you want to operate on the far right. You want the best image possible because you've got to remove the tumor, and don't remove not the tumor, but remove all of the tumor. You have to identify tumor, you have to identify not tumor. And so you want to go from this image across, because you're going into the operating room. Which of these images do you want? You get that image through collaboration. You get that image through working across medical institutions, medical researchers around the world, and you get that. But the problem has been that you can't collaborate globally, because to do that, you have to share sensitive patient information. You have to share data on patients in your institution with other institutions, and you can't do that. So if you want to protect privacy, this is the image you're going to get. If you want to collaborate, that's the image you're going to get, right? This is an example from medicine, but this applies in financial crime as well. Our ability to build on the previous two speakers, our ability to do a better job of detecting financial crime, of taking that $270 billion spend and getting a good result of it, comes from solving this problem. We want to move towards collaboration, but there seems to be this trade-off on collaboration and protecting data. So, less serious than brain tumors, we're going to talk about chihuahuas, okay? So let's say that we want to build an AI to detect chihuahuas, okay? Much more pleasant conversation. So here's how it works. I'm going to take a whole bunch of images of chihuahuas, and then I'm going to take a whole bunch of images of not chihuahuas, and I'm going to run them through an algorithm. And that definition of chihuahua, not chihuahua, is machine learning, right? So when we say we need more data to train better models, we're talking about this. We want this data, if we want an algorithm, if we want an AI to detect chihuahuas. Right? Everybody following? Okay, so here's how you would test it. This image is an internet meme that I took from somebody else, but I love it. It's brilliant. It's chihuahuas and blueberry muffins. So we're going to test an algorithm. So on the last slide, we built an algorithm to detect chihuahuas. But we want to make it really hard for the algorithm, so we're going to give it test data of blueberry muffins and chihuahuas, and we're going to see how the AI distinguishes between chihuahuas and blueberry muffins. And if you know data scientists, if you know people who are playing around in machine learning and computer vision, this is actually a somewhat common test, is the chihuahuas muffins, believe it or not. So you take the test data, you run it through the algorithm, and the output of an algorithm is a distribution. Okay, this is one of the ways in which the world is changing inside of a bank. You might have a rules-based system which just creates two piles. You've got the positives and the negatives. In the algorithmic world, in the AI world, we get a distribution that comes out of it, right? So this is our algorithm saying more like Chihuahua, less like Chihuahua, and this is the rank ordering, or the number of images, more and less, right? So what we do is we have a human, we have one of the experts come in and look at it very closely and say, yep, algorithm got it right, got it wrong, right? So, and then you measure your performance. So you've got this distribution from low to high, and then you've got your count. So what we would do is, let's say that we're going to draw a threshold here. So we're going to treat everything to the right of here as an alert, as if a chihuahua, as if a brain tumor, as if a money launderer, as if a terrorist, as if a human trafficker. Whatever the case may be, this is how AIs work. You have to set a threshold, and then you human review. You need the expert to come in and score it, to human review it. So here we would say, you know, Chihuahua, 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 and then there's a blueberry muffin here. So these are called true positives. So predicted positive. So if it's this side of the threshold, it's predicted positive for Chihuahua-ness. And if it's a Chihuahua, predicted Chihuahua, it's a true positive. That's a false positive. Now, if you work in industry, if you work in the financial crimes compliance industry, the worst part of your job is false positives, right? You have too many non-criminals that are alerting as if criminals, too many money launderers alerting as if money launderer, but they're not. Likewise, if you have a not Chihuahua over here, it's predicted negative, and it's true, so it's a true negative. And if you have a Chihuahua over here, it's a false negative, predicted negative, but false, right? So for those of you who are not academics doing math on AI, very, very simple to judge if it's working. You go through this process and you count your true positives, your false positives, your true negatives, false negatives. That's it. And then you can do ratios and you can measure your efficiency and effectiveness, right? This is how you judge AI systems. There's lots of talk about transparency, explainability in the AI world. this is how we solve it. We look at the inputs, we look at the outputs. You don't need to understand advanced math and how a neural net works, because most of us in the world will never know how a neural net works, but we can look at the input, we can look at the output, we can measure it, okay? So, in the real world, we're gonna have a lot of data, a lot of muffins, a lot of chihuahuas, a lot of images of brains, lots of data on bank customers who may or may not be money launderers. You get an output. It might look something like this. Okay, so the pictures that are in color are your chihuahuas, are what you're targeting, are your money launderers, are your human traffickers, are your drug traffickers, are your arms exporters without a license. And if it's grayed out, it's not a chihuahua, right? So you still might draw a threshold and say we're going to treat everything above a certain number and we're going to treat it as if positive, predicted positive. In the world today, especially in this $270 billion financial crimes world, you get distributions where there are very few true positives above the threshold. There are a lot of false positives above the threshold. And financial institutions spend an awful lot of money trying to find the criminals. And that's why we spend so much money globally per year, and we have such little impact on financial crime of all kinds. What financial institutions do today is they move the threshold. So if you're the CEO or the CFO of the bank, you want to cut those costs, you might want to move the threshold this way, so you're reviewing fewer cases. If you're a bank regulator, or if you're in law enforcement or national security, you might want to move this way, because there are some false negatives you want to catch, right? So this is the trade-off that happens day to day for the past couple decades in this industry. But with AI, what we can do, instead of just having a debate about where's the threshold, we improve the algorithm so we get more of what we're looking for to the right and more of what we're not looking for to the left. So ideally, you would have everything that's not a chihuahua off to the left and everything that is off to the right, and then it becomes very easy. So that's what we're pushing towards. That's the world we want to live in, where financial crime of any type, it could be fraud, it could be money laundering, it could be export controls violations. It's easy to identify it because our algorithms are so good. So what you do, the process today is, in the machine learning world, is you have your training data, you build your algorithm, and then you take your production data and you run it through it. That's the process I just walked you through. But after you run through it once, and you know where are your chihuahuas, you have labels that you then feed back in. Your training data just increased. You have more training data, you have more training data, now you can build a better algorithm. This assumes you're working on your own as a bank, as a financial institution, as a medical researcher on your own. You can get better. It's a good system. It's a nice system. But it's not good enough. So, in federated learning, what is federated learning? In federated learning, instead of, we're going to collaborate. But we're going to collaborate without sharing any data. In federated learning, we share the compute. We share the algorithm, not the data. So in this example here, you've got a hub. And in the hub, we call it, at Consilient, we call it the algo factory, the algorithm factory. And the algorithm goes to a financial institution. It runs. The people at that financial institution go through that process on the last slide where they run it, they measure the performance, and then they identify additional training data, and then they send it back. Just the algorithm. No data moves. No data moves. No data moves. Just the algorithm. Means, variances, velocities, the types of data you would have on types of target transactions such as fraud or money laundering, pump and dumps. What would that look like? What would a pump and dump look like? We measure the behavior. We send it to the bank. The bank goes through the process, and they identify additional labels. They train it, they improve it, they send the improvements here. There's a validation process that happens. Goes to the next bank. Bank benefits, improves, sends it back. Validation, next bank. Uses it, improves it, sends it back. Next bank. Maybe one of these nodes instead of a bank is a government agency. Maybe it's financial institutions within a global institution like a Standard Charter where you can't send data across borders even though you have bank branches around the world. You can still share an algorithm. So there's lots of ways to think about what those nodes are. It can be a collective of financial institutions working together in Korea. It could be a Korea-United States partnership. It could be public-private partnership, financial institutions with government agencies. It could be within a large global institution. And this is what federated learning is. So we're sharing the model. We're getting the benefit of all of the training data of all of the participants without sharing a bit of the data. But the model benefits as if the data were shared because we're sharing the model. Oftentimes, the simplest ideas are the ones that change the world. I think this is a simple idea that is transforming the world. Don't share the data, share the model. That's it. Oh, I forgot. Look at it. So, you remember I asked you to pretend you're a surgeon and this idea of the trade-off, right? You're going into surgery, which image do you want? I think this is very exciting. So this is the journal Nature Communications. So the journal Nature is one of the top global publications in the world. This is about a year old, is all this article. And this is a brain tumor that is the most deadly brain tumor to humans in the world. And it's also rare. It's a rare brain tumor. So any one medical center or research institution will not have a lot of data to build models to detect this tumor. But if a human gets this, this is the most deadly to humans brain tumor in the world. 6 continents in the world contributed to this study to develop that image on the right. 71 institutions around the world. They had images on 6,314 patients. So you get from here to there by looking at data on 6,000 patients, but it takes 71 institutions around the globe to get there. Korea, the United States, Europe, Africa, Asia, everybody's participated. 33% improvement in identifying the border of the tumor, so that now surgeons anywhere in the world get this 33% increase that, but for global collaboration, would not have happened. And no patient data was shared. I love this article, not that I'm involved in medical research, but because this sets the path for every other regulated industry you could imagine. You've got an industry where you are not allowed to share data or you don't want to share data. There's several studies in medicine and biomedical research that demonstrate federated learning provides these types of results in the absence of sharing data. So, federated learning and user-centric AI. From, I believe, Professor Lee's talk from 2 events ago, what I got was no personal data shared, no centralization of data, and expectations are exceeded, right? So what we're doing in financial crime at Consilient is exactly as I showed you on that last slide. We have a hub. Right now we've traveled an algorithm across 4 different banks. And as we do this, no personal data ever leaves a bank. We don't want it. There's no centralization of data. If a financial institution has their data in a server farm in the basement, if they have it in a commercial cloud like a Google or an Amazon, we don't care. People put their data wherever they want it. We don't care. We want the algorithm to be able to travel in and out, and we want them to be able to inspect the algorithm traveling in and out to make sure that there's no data coming in or leaving, and the performance. So this is our empirical evidence. We're not yet published in Nature or Science on this, but these numbers are pretty recent, and I'm sharing them with you today for the first time in public. So if you go into a financial institution that is responsible for managing financial crime risk, they'll have a rules-based system in place that they've been operating for the last 20 years. So pre-machine learning, pre-AI, rules-based, a bunch of if-then statements. If more than $1,000, if after 2 o'clock in the morning, if this, then alert. In this example from one of the 10, 15 largest banks in the world, the algorithm had traveled to 4 banks. This is the 4th bank. They had a system where they had 800 alerts per month. So think about the chihuahuas, to the right of that threshold. So they were alerting on 800 per month. And that 800 per month, by the way, was yielding about 10 or 15 true positives per year. So massive investment of time, energy, resources, generating almost no good outcome. So that's what it looked like. So here you have the number of alerts per month. And here you have your true positives, the known bad actors. That's 100%, because they didn't know what they didn't know. So they're finding 100% of what they knew about, looking at 800 per month. Then they hired a machine learning team to work internal to the bank, their own machine learning team, because institutions are hiring data scientists, they have AI, they have machine learning, they've got a team, they've got a cloud, they've got tools. Their internal team went from 800 alerts to 500 alerts per month to find the same true positives. Same yield, 100%, 800 to 500. AI is great, right? That's awesome. As I said earlier, it's not good enough. We came in with the federated model, the traveled model, the federated learning AI, and we brought it down to 170 per month. So 800 per month went to 500 per month, just going from rules-based to AI. With one of the largest banks in the world and an elite team of machine learning experts, they went from 8 to 500. Our team is not smarter than their team. It's not about how smart your data scientists are. It's about how much training data you have for your algorithm. The traveled algorithm went from 500 to 170 alerts per month to generate the same output. And then the best part of this is because you now have that much extra time, energy, and resource available, you can find a lot more risk. So the bottom line of this study, and again, this is new that I'm telling you all today, is there was a 78% decrease in effort. So 78%, so 800 down to 170 is a 78.9, maybe 79% improvement in efficiency. And it was a 600% improvement in effectiveness. So they found 6 times more risky customers working 80% less. Right? So similar to the types of outputs that you would want to see to make the investment in switching from an embedded system to the newer system. So my sense on the call to action is we should be pushing every day for more collaboration. More collaboration. Again, it's one of these things that is so obvious that we shouldn't have to be told it, but we all get more done when we work together than when we work on our own. So let's collaborate. In the AI machine learning world, collaboration does the same thing. It's what we want, it's what we need. We need to collaborate. And following the lead of President Park, who quotes Adam Smith quite often, and I'm also an economist and followed his lead last time, the idea from the last conference was that the division of labor wealth comes from the division of labor. I would add, book 1, chapter 3, is that increase in wealth is limited by the size of the market. That means the more institutions that can collaborate around the world, the better this is going to get. So that's the first point, is we should push for that. And I think this U.S.-Korea partnership that we've launched is a very exciting step in that direction. It's going to help us make a lot of progress. And then the second is do this consistent with the UCAI design principles. Thank you very much.